Now that we've had a bit of a look at entropy, let's go back and consider engines again. So in particular, we'll be looking at entropy changes in engines and their efficiency. Now this is useful for you because efficiency comes up a lot in the junior science syllabus. So possibly you won't want to go into as much mathematical detail as we will here, but having a really deep understanding of what the efficiency of an engine actually means will help you with your junior science teaching. So let's start by defining exactly what we mean by an engine. So an engine is essentially something which extracts heat from its environment, the surroundings, and it converts this heat into useful work. Now, central to every engine is a working substance. So for example, in a steam engine, the steam is the working substance because it's the steam which expands, which does the work, which is the useful work that we can actually extract and use. Before we looked at gasoline engines. In the gasoline engine, it's the air-gasoline mixture which is the working substance. A good place to start our consideration of engines is with an ideal engine. So an ideal engine is one in which all processes are reversible and there's no wasteful energy transfers that occur, such as energy transfers to friction, air resistance, or turbulence. So one of these first ideal engines which was studied is known as the Carnot engine. This was actually studied before we developed the first law of thermodynamics and a good understanding of entropy. So a Carnot engine is special because in principle it is the most efficient at converting heat into work. So that's what we want. We want as much work as we can get for our heat. Okay, so what I've put here is a schematic showing you what a Carnot engine is. So the Carnot engine has the working substance, which is the gas, which you can see as a little rectangle there with arrows around it. And that's showing that this gas undergoes a cycle. So in a minute, we'll look at what that cycle is on the PV plot. The other important parts of this Carnot engine are we've got a heat reservoir up the top, the pink heat reservoir. This is at some temperature, TH, and it's providing some heat flow, QH, into that working substance. Now, some of the heat is released by the working substance. So you can see that going into the cold reservoir down the bottom. So that's given the symbol QC, and the cold reservoir is at temperature TC. And then we've got the work coming out. So the work coming out, that's what we want. The whole aim with engines is to try and maximize that amount of work. Okay, so let's have a bit of a look at this shown on a PV plot now. Okay, so let's have a look now at the Carnot engine on the PV plot. So to start with, I've just got my blank PV plot and I've drawn on two isotherms. So up the top here, we've got TH. This is an isotherm at temperature TH, which is the temperature of this hot reservoir here. And down here, we've got TL, the L standing for low here, and that's at the temperature of this colder reservoir down here. Now we're going to go around the cycle this way. So we'll start up here where we're absorbing heat at the constant temperature. So let's call this one point A, and the initial process is absorbing heat isothermally like that. So we'll go to state B. Now physically, an example of how we could do this is if we put a piston of gas with a constant weight force on the top, so constant pressure, and we allowed that piston of gas to come to thermal equilibrium with a hot reservoir underneath it. That's an example of the type of process that we're talking about here. Now in this process we've had an expansion in volume, so the work done here is less than 0, and because the temperature hasn't changed, the change in internal energy is equal to 0, and so positive heat is flowing into the gas, which is what we said. It's a heat flow into the gas. Okay, so the next process that we undergo in our cycle is actually an adiabatic expansion. So the next process does not involve any heat transfer. And this is where we will get the work out of our gas. Okay, so the gas is going to expand adiabatically like that to point C here. So this is adiabatic. Adiabatic means Q equals 0. We know if Q equals 0 that there is no change in entropy in this state because entropy is equal to Q over T. Okay, so now we've had our adiabatic expansion. What we'll do now is we'll have an isothermal compression. So here we go back to a smaller temperature, a smaller volume still at temperature TL. So it looks something like that. In this case, the work done is greater than 0. That's the work done on the gas. Change in internal energy 0 like we had up here. And so Q in this case is less than 0, just because we know that our change in internal energy is equal to Q plus W. And then finally, up this side, we've got an adiabatic compression. So that's going up like this, adiabatic. And so that's once again got Q equals 0 by definition of adiabatic. And so there's no entropy change on that side as well. So this is the PV plot which represents our Carnot cycle. Okay, so let's have a look at work and entropy in a bit more detail now. Let's look at work up here. Okay, now around this cycle from A to B to C to D and back to A, we know that the total change in internal energy is equal to 0 because internal energy is a function of state and we end up back where we started. Okay, so we know that's equal to 0. We also know that it's equal to the amount of heat added around the cycle plus the amount of work done on the gas around the cycle. So this tells us that W, the amount of heat work done on the gas, is equal to minus Q. And we know how much heat is added to the gas because from A to B, we've got a heat QH added. So this is equal to minus QH. And then from B to C, there's no heat added because that was adiabatic. So by definition, Q equals 0. From C to D, we've got heat coming out. So QL is heat, but that's flowing out of the gas in this case. And then going from D to A, we've got no heat flows. So around the cycle, the amount of heat that flows is equal to the difference, the absolute value of Q minus the absolute value of L. And so this is the work done on the gas. So the work that we get out of our engine is the work done by the gas. So work done by gas is equal to QH minus QL, i.e. the heat in minus the heat out. Okay, now it's also useful to look at the entropy. Now, and once again, entropy is a state function, so we know that around the cycle, we're getting back to the same position. So we know that delta S is equal to 0 around the entire cycle. We've also seen that delta S is equal to 0 for both these adiabatic processes. So all we need to worry about is the change in entropy going from A to B and from C to D. And previously we showed that for isothermal processes, the change in entropy is equal to Q over T. And so we have delta S when it's attached to the hot reservoir is equal to QH over TH. And we have that when it's attached to the cold reservoir, it's QL on TL. And so we know that these two things have to add to give 0, i.e. they're equal and opposite. So what we can write is QH on TH is equal to the absolute value of QL on TL. And what we'll be able to do now that we have this expression for the work done and this expression relating the heats to the temperature is derive an expression for the efficiency of the Carnot engine.